Good morning. I see my students ready, ready to learn. Good, good. Good morning, good morning. Okay, let's just carry on with the calculus, with the derivative, because now we know that magic word, derivative. Okay, that means this was the last question, I believe, that we did. And what we learned from that slide, that exercise. Can you remind me? Absolute value of x. What is the specific thing at one point on that graph? Do we remember? What is happening at 0 with respect to derivatives, of course? Yes, we have sharp angles, sharp turn, and actually, okay, no derivative, because that limit, this limit is the derivative. But actually, oh no, function is still continuous. That means this is a little bit, I can use different color. What about just the limit? X is approaching 0. And what is the limit of absolute value of x as x is approaching 0? Yes, it is 0, because we can see function is approaching that sharp corner. That means with respect to just limit and continuity, no, function is continuous and the limit exists. Different type of limit doesn't exist. Let's use maybe this color. This, of course I cannot. This limit. Let me move this. This limit doesn't exist, which this limit represents the derivative. Yes? Derivative does not exist. That means always when we have sharp corners, sharp turns, derivative is not defined. Okay? That means that's important. Let's look at the next, this is the solution. Let's look at the next function. Similar thing. Cube root of x taken to the power of 1/3. Is this function differentiable at 0? This is the shape. Yeah, this is one of our magic functions that we supposed to know the shape. And I don't know if we can figure out what is happening at 0. We do not see the sharp turn, sharp corner. But what is happening at 0? We can definitely compute the derivative. We will, through the limit definition. Also, x and y approaches 0. Yes, that's if we compute a limit, again, that's correct answer. What color I use? Purple. Okay, let's be consistent. As x approaches 0, cube root of x, which is the same thing, is 0. That means yes, y is 0, x is 0. We have limit at 0, function is continuous. But now with respect to rate of change, with respect to the derivative, maybe the slope of the tangent, we can also call it this way. It's changing from positive. Do you think we will have negative slope? Because how we can think, we can always try to draw a tangent lines. Tangent line, tangent line, tangent line, tangent line, tangent line. And each of them, they are not so steep, probably small value, but they are positive. That means I don't know if we will have negatives, but something is definitely happening. Okay, because I'm asking, yes, this question. Okay, one thing, what we can try. Do you remember what was cube root of x is an inverse function for what function? What function we have to inverse to get cube root of x? Maybe this will be easier. Yes, x cube. Thank you. That's when we have function x cubed, you can use blue. Function x cubed looks like this. Oh, I did even too much. But I still want to. Okay, and I don't know if we remember, but at zero, cube root of x has horizontal tangent. Okay, we will prove this maybe even today. Now you just have to believe me because I just want to solve question 12. Okay, that means at zero, at x equals to 0, is a horizontal tangent. Horizontal tangent line. Slope is 0. I don't know if we can really see this from the graph, or maybe we just have to probably know this, or yeah, we will prove this. But now, what is my point? If it's horizontal tangent for x cubed, what do you think? What will be the position of the tangent line to the inverse function? Vertical, yes, because horizontal, vertical, we inversing. That means we do have at 0 is a vertical, and that's true. Vertical tangent. Yeah. We just got this from the inverse, yeah, from the inverse property. Okay, and now vertical tangent. What is the slope of the vertical lines? Also algebra question, and I'm sure you know. Undefined. Yes, because we can see vertical. They don't really, yes, we don't have that. We have rise, but we don't have run. Rise over run. Run is 0. Yeah, we're not dividing by 0. That means a number, a constant over a small number, let's say 1 over small is big. That means that slope, and we can see so steep. We can call it like even infinity. Of course, we're not calling infinity, we're saying undefined. But yes, vertical tangent, vertical lines, actually, they don't have slope. No slope, no derivative. That means this is the reason. If you will possibly know, or let's say that the graph will be like indicated that at this point we have a vertical tangent, or it will be nicely like pronounced, like explicitly draw, you can say no rate of change at this point, no derivative. No tangent, no slope. I mean, it is a tangent, vertical tangent, but no slope, no derivative. Okay, that's implicit. That's another thing. Sharp corners and vertical tangents. And one more thing. Discontinuity, actually. I don't have to keep a secret. We have basically 3 things. Again, sharp corners, vertical tangents, and discontinuity. Yeah. No slope at this point because no tangent or vertical tangent, no slope, no derivative. Okay, but what we can do, we can really quickly compute. This is function g. G prime at 0. That's the derivative of the function at 0. And we learned yesterday, this is the limit. Let me put this. H goes to 0. G at 0 plus h minus g at 0. And again, that 0 is different than h is approaching 0. H is the distance between these 2 points. We remember that? Okay, and let's see what we can get. Okay, function is cube root of x, but we will substitute that input, cube root of 0. Oh, that's... And what we have? We just have cube root of h, that's 0 over h. Nice, because we may rewrite this is h to the power of 1/3, this is h to the power of 1. What we can do with the exponents when we dividing the same base? We may subtract, yes, it will be 1/3 minus 1. I can write Can you help me with that fraction? It will be negative 2/3. Yes, thank you. And I can rewrite like this, because then we like as a fraction without a negative exponent. Now we can see 1/0, 1 over small number is a big number. And infinity is not existence number. This limit does not exist. The conclusion is derivative does not exist. We prove nicely through the definition, and graphically we know the meaning. Yes, vertical tangents. Yeah, that's mean when you see this, yeah, function is not really, I mean, it is changing rapidly, but we don't really, yes, we no, it's no rate of change does not exist as a finite number. We can still make some other like analysis, but no, derivative does not exist. Okay, that's we know this, and that's the solution. Okay, that's mean this is actually the end of, maybe we supposed to do this yesterday, but I have one more question, one more exercise, because this is practice. You can go through, you will solve all of them and you can check the solution. But I have this question. Okay, let's do just these fives. I want my students to help me with this, and then we will jump to section 3.2. Okay, that means this question is asking the other way. Yes, I'm testing if you know the definition of the derivative, and this is good for the test, yeah, the test question. Okay, that means the instruction is telling us that each of this limit represents the derivative of some function and at some number a. And we just have to state what is the function and what is the number a. Okay, that's me. What do you think? Number one, what function? This represents the derivative at the point a. I don't know what is a, and I don't know. Okay, I have to stay. I will erase, and I have to state a function. Do you see? It's kind of backwards. Okay, okay, let me come back for a second what we did. Do you see this one? That's what I am asking. Like I am providing that, I mean different functions. I am providing that green box, green limit. Limit as h goes to 0, cube root of a plus h, a is 0, minus cube root of 0, which is f of 0 plus h minus f of 0. Actually, f, g, the same thing, over h. That's me looking at this, you know, yes, we know that this is derivative of the function cube root of x, cube root of x. Yes, function is actually, I can cube root of x, and the number a is 0. That's what I'm asking. What is the function and what is the a? Let's go, because kind of like backwards. Okay, one more time. Yes, now you can. It's important. It's really important because, yeah, we have to always work forward and backwards. Yeah, we always have to be flexible. Then we understand the concept. Okay, Lara, what did you say? Yes, it's definitely x to the power of 10. Really good. And the a value is 1. 1. I can say 1, or I can even remove this because that's the perfect. That's what I want. Okay, next one. Derivative at which point and for what function? Do we see? 1 over, and that's the input. 2 plus h minus 1. It's 1 over x, 1 over x, and the a is 2. Good. Yeah, please try identify this. Yeah? Then you decoding the magic. Okay, what is this function and what is a value? Okay, who can tell me? Even if you're watching this later, you can say aloud or you can write it down before, or you can pause the video. Yeah, I will know that you did this. Everything is energy. You know how I believe in this. Okay, what is number 3? What function we see? Yeah, I think the first, yeah, it's the fourth root. Fourth root of x, or x to the power of 1/4. That's also good. And the a is 16. Yes, please not be like the next quantity, the subtraction, because fourth root, what is fourth root of 16? Fourth root of 16, it is 2. Yes. Okay. Okay. Another one. Derivative for what function and at which point? Yeah. We can see the input. Yes, we can see f of a plus h. That means this is right away f of a plus h. It's 2 to the x because everything is placed in the exponent. And 5 is a. And this is 2 to the power of 5. 2 to the power of 5 plus h. It's okay. And the last one, please tell me the last one, and we will be done with this section. What is the function and what is the number a that we're looking at the derivative? Yeah, it's somebody, everybody is helping me. I know that you know, I know, I can feel it, but just typing, Yes, thank you, Laura, tangent of x, yes. And the number is pi over 4. And what is tangent at pi over 4? Tan at pi over 4, of course, 1. Yes. Okay, thank you. Thank you for participating. And yeah, thank you for being on duty. Yes. Okay, great. That's it. And I have more, but we can, yes, you can. I think I have 6, 7, 8, but you can try. You can try this later. Okay, I will switch. I will switch the presentation. I will stop sharing this and I will share. Oh, am I ready? I am ready. I will share this. Beautiful. Okay. Oh, I don't know. Oh no, I want to. Something is wrong. Three 3.2 because my screen. Okay, am I sharing? I am sharing, right? Yes, okay. Because I have two screens and sometimes when I share covers the entire screen, I don't see anything. But you know, I always log in twice to see the chat box and to see my students because I can see you. I know what you're doing. Okay, now, yes, we will climb next level. We will try to define derivative as a new formula, new function. Okay, because so far, what we know about the derivative, what we learned in the previous section, what is derivative? What we learned yesterday? The derivative is, tell me we have a couple of things. We can say instantaneous rate of change, yes, instantaneous rate of change, but in general, which instantaneous rate of change, slope, yes, slope of the tangent, slope of the curve at that point. That's mean what we learn, yes, just f prime, yes, everything, instantaneous rate of change, because instantaneous means at that point. That means we did learn this, yes, derivative of the function at the point a. Yes, and when we calculate the whole limit, it's a constant. Yes, it's actually a number. Yes, we can say it's a slope. It's a slope. It's the instantaneous rate of change. Yes, but everything, it's a number, it's a exact value. We can calculate and we can have value. We will not have suddenly a formula because no independent variable. Yeah, that's that's the derivative slope, instantaneous rate of change. Yeah, that's for now, that's okay. F prime, we can say F prime because I see. Okay, now what we will do, we will try to remove A, like we will try to remove A. I mean, not remove, we will let A to be actually a variable. That means we will change A for X. That's what we will do. In all of the, we will repeat the whole process, but instead of A, like exact point where we are, we will let A to be X. And now this will be more general solution. It's still that formula because the answer now, the answer will be in terms of X. Yes, like let's say will be another function, let's say K of X, yeah? A new derivative as a new function, I suppose to say new function. That means we will have expression with like in terms of X. This expression still represents the slope of the tangent or instantaneous rate of change because we have different angles to look at this. Yeah? But now we can pick, like we have the general formula of the derivative, and let's say we would like to analyze what is derivative or what is the slope of the tangent at 5. Then you will substitute 5, maybe at 500, maybe at -5. Okay? That means that we will have a little bit more general. Everything will be the same, but it will be a formula for the derivative. Okay, so now let's see, that's old. I mean, not old. This is derivative at the point A. We can see A, f prime at A. And as I said, this will be X, this will be X. We will let A to be a variable. This will be X. Basically, this is here X, f of X. Now you can probably realize why we have this H expression, yes, because the point Q had the coordinates X. Now, yeah, oh, another one, X and X. Okay, let's see. Oh, I suppose to type X here. Okay, I have to change this. X and X, okay, but we do have it. That's now we can see we will do exactly the same, and we can even solve a couple of derivatives through the limit, but then the final answer will be a function because it will be the expression in terms of X. Okay, f prime of X is still derivative, still the same understanding, the same meaning behind this, but in terms of a variable, it will be a function. Okay, let me know, I have a couple of notes. Yeah, it's still slope of the tangent, even, yes, even if it's in terms of X. Yeah, it's called derivative because it's derived from that limit. Domain, sometimes because we're dealing now with a new function, that means each function has a domain, the set of X that we are allowed to substitute. We have to look at the formulas because the formula changed a little bit. That means sometimes derivative has a little bit smaller set of x's, yeah, smaller domain. Because we're doing, yes, a little bit of algebra. Yes, and the new function is called derivative of f, and yes, for each limit, yeah, assign the number, yeah. Okay, easy notes. And let's start, because we will try to find a couple of derivatives as a new function, and hopefully we will find a pattern, and I will introduce one formula, one important formula, and then we can skip the limit way. Okay, the first function that I choose, nice and easy, x. Find the formula for the derivative f prime of x. But please tell me, what is the derivative of x? We don't have to do anything because it's linear function, and we know what is. Yes. And y is 1? I just want to hear that answer. Y derivative of x is 1? Because of the slope. Thank you. That's perfect. If you answered in your head, like when you're watching this later, because of some formulas and your brain is like on fire, no. Please don't, because this, yeah, we complicated. Derivative of x is 1 because the slope is 1. Perfect. And We can still do through the limit. Let's see. Yes, I evaluated f of x plus h. Now we can see no a, x plus h. We may subtract, and h over h is 1. Yes? But of course, we don't even have to do it. Slope is 1. Okay, that means derivative of x is 1. Actually, it's a constant function. What we will also do, maybe I can do it really quickly in between. This is function x. Let's say x. That's x and y. And since we are finding a derivative as a new function, we can also draw this function. And now derivative of x is 1, which is just a constant function. Right? That's now because what we have to know kind of like the connection between the graph of the function and the graph of the derivative. And what we always have to think about the slope of the curve. That means the slope, if I would like to plot the points, let's say for a couple of like all of this, like negative 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what I will do, the same for this one. That means I just have to find the values of the slope. That means when I will, for negative 10, let's say, the slope is 1. For negative 9, the slope is also 1. 1, 1, 1. For each of this green dot, yes, the slope is 1. Then I will plot that value. For that value, the slope is 1, 1, 1, 1, 1, 1, 1. That means, and then I can connect. That's how the graph, like graphically, yes, graphic. That's we know, yes, we know the limit and we know also the graphical connection. Okay, next one. Next one is x squared. Yes, x squared is not a linear function and the slope of the x squared is not constant. That means what we will do, we have to really, we cannot really guess the formula. Let's do it. Did I type? Okay, that's the derivative. I mean definition, limit as h goes to 0, f of x plus h minus f of x over h. Let's evaluate. F of x plus h means that we have to substitute x plus h to the formula. I did. And this is f of x, which is x squared. Let's expand this. Now cancel out. Now factor out h. H is the problem. H is the 0 over 0. Gone. And the direct substitution. Now we can substitute instead of h0. We have the formula. Derivative of the function x squared is 2x. Yes, that's what is the slope? Do I have, okay, I can, what is the slope? Let's do the connection really quickly. I mean, we have the formula, that means it's function is x squared. What about derivative? Y prime is 2x. That means what is the slope at 1? Let me use green color. What's the slope of the tangent or slope of the curve at 1 for that parabola? This is slope, yes. This is f prime, but it's also, yes, it will be 2. That means slope will be 2. I can draw the value 2. Yeah? I kind of know that this will create, let me follow, 2. What about the slope at 2? What will be the slope of the tangent? It will be 4. Yeah, we're just following the formula, the general formula, 4. Okay, at 2 is 4. And then so on. At 0, what's the slope at 0? 0 times 2, of course, is 0. And for negative 1, let's give me for negative 1, of course, we can see is decreasing. It will be negative 2. For negative 2, it will be lower, negative 4. Yeah? And then if we will find more points, we can definitely, yes, plot all of them. And actually that's the graph. Sometimes, yeah, we will probably be asked at some point, having like seeing the graph of the function, then you have to sketch the draft of the derivative. Okay? But let's look at one nice thing. This is parabola. Yes, parabola. For all of the negative numbers between negative infinity and 0, I mean this part, purple, let's use purple. What is the value of the slope, positive or negative, on that purple part? Negative, and you can see the graph of the derivative is below the x-axis, has negative values. Perfect. And what about the red part? Function is increasing. Function is increasing. What will be the slope, the sign of the slope? It will be positive, yes, positive. And we can see the graph of the function is above the x-axis, is positive. That means now will be also important to think increasing, decreasing, and positive, negative. Because we can see function x squared is positive everywhere. This is positive, is above the x-axis. Yes, above the x-axis are positive values, but has negative slope and then positive slope. Yeah? And this is different, negative, positive. Yeah, that's the connection. Okay, let's come back. That's when we kind of alternate formula and the graphs. Another one, x cube. X cube. Do we know how x cube looks like? I'm just thinking about the graph. We will get the formula, but x cube, yes, looks like this. X cube looks like this. Okay. And what do you think? What will be, this is x cube. And we don't have to get the formula. Maybe it's, yeah, but how, maybe this question. Will the derivative be a function above the x-axis or below the x-axis? Maybe that's helping. Above, that's you can see. Let's say you have to match some functions and derivatives, then you will know. Don't pick the function that is below, because it's all the time the slope is positive. Slope is positive, function is increasing. That means definitely function will be placed, I don't know, but will be placed above. Yes. Okay, let's find the formula. Then you will kind of like, because it's also helping, yes, the other lens when we look through the other lenses. Okay, that's the only tool. Limit definition. Let's evaluate for x cube, x plus h cube minus x cube over h. Let's expand the cube. Yes, let's FOIL 3 times. Oh, I draw it here. I mean, okay, I can erase. Okay, because it's long. Yeah, you can expand this right away, or you can FOIL 3 times x plus h times x plus h times x plus h. And now we see what we see. I cancel out this. Now we can see h in each term. We can factor out, and this is the common zero. Gone. Okay, what is the final answer? H is 0 because we have no more 0 in the denominator. That means this is 0, this is 0. The final answer is 3x squared. Okay, that means actually it is parabola. It's quadratic function and makes sense. Parabola is positive. Okay, that means when we will try, and we can still predict, oh, this is supposed to be horizontal tangent, do you remember? At 0. We will also, that means this is x cubed. And its derivative, or maybe the value of the slope, the tangent line, it's x squared. 3 is a little bit slimmer because each value is multiplied by 3. Y prime is 3x squared. Okay, 0, it's 0, and then, and we can see this slope will be really steep, really steep, really steep, and actually it's approaching from the steep slopes, we're getting really small, 0, and makes sense. From the big values, we getting smaller and smaller. And then again, from the not really steep lines, the slopes are getting really steep. That means the values from 0 are getting bigger and bigger. And yes, makes sense. The parabola shape makes sense. Okay, now, okay, let's do this one because I still have to finish with formulas. We have time. Okay, 1 over x. 1 over x is also interesting. How 1 over x looks like? Let's think. 1 over x is hyperbola in the first and the second, first and the third quadrant. And is the slope always positive or always negative? What do we see? We see decreasing function, decreasing, negative, negative. Okay, that means the formula, we expecting the formula for all of the values of x, except 0, because we can see 0 is not in the domain. The formula and the graph, the same, must be negative. Okay, negative. We can we predict the graph? This is y, and let's say this is y prime. This is, what is the slope here? Small, yes, small, really small, not steep, small negative. That means somewhere here. And then it's getting steeper and steeper in the negative direction. That means I will say something similar. Something similar. Let's look at this one. Slope is big. Yes, that's big negative, big negative. That means we will start here. And then, 2, and then it's getting actually less steep, means the values are smaller, but still negative. I think something like this. Okay, but let's see. Definition, limit definition. Let's evaluate for x, 1 over x. Let's get the common denominator. I think we did this exercise yesterday and in chapter 2. Did I multiply? Yes, that's always my tricks. I am multiplying by the common denominator, and then I nicely simplify the double fractions, distributing, and then canceling. Now we can cancel that h, and we can substitute 0 now. -1 over x squared. And makes sense because this is the derivative. It's x squared is always positive, negative makes always negative. Yeah, then I mean the negative sign. And do we know function x squared? Hyperbola in the first and the second quadrant. If it's negative, we're doing the reflection. That's actually what I just draw it. And this is function 1 over x. Yeah, also makes sense. But we kind of predict. Okay, we have, yes, and we can, yes, now we can have more and more and more formulas, and you can do it this way. You can find the formulas for the derivative. But what we will do, okay, we will skip this one. You can try the same process. Oh, and it's a graph and the derivative. Let's maybe look at quickly. Just really quickly, because I know that this is also a big part of this section. This is function, and that was the formula. We don't have to know the formula. You can look at later. And if I will ask, draw a derivative, sketch the graph of the derivative of this function, what we can do, we can always start with the horizontal tangents, because at that peak, yes, at that we call maximum minimum, but yeah, not yet. It's definitely tangent is horizontal. What's the slope of the horizontal? What's the slope? Yes, 0. That's you can see at these points, we will plot 0. Because derivative is basically the set of points that corresponds to the slope of the tangent line, slope of the curve. Okay, and now the same. Function is increasing. That means the slope is big, 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 and it's approaching zero. That's when we have big number, big numbers, and approaching zero. Now the slope is negative. And it's actually interesting, from zero through some negative values to zero. From zero, negative, zero. That means from zero, some negative values to zero. I think in the middle, we have this maximum steepness in the negative way. That's mean we have to arithmetically think it's smallest value, yes, because this is the smallest. But we can see in the middle, we have the steepest line in the negative. And then again, it's getting less steeper, meaning that we have to get higher values to get zero. And starting from zero, not really steep, and then really steep. The values are increasing big. I hope you will, yes, you will draw this. Okay, but now what I want to do, okay, another one, square root of x and its derivative. Yes, derivative of the square root of x is 1 over 2 square root of x. You can do it, yes, and you can analyze the graph and the derivative. You can try this one. You can try this one. Or you can check the solution, okay, on Canvas. Okay, what else? Because the formulas, you have to help me with the pattern. We also have the other notation. Let me show you. Okay, we definitely using this notation. That's not a problem. We also have a notation that is called Leibniz notation. Yes, he was working, and this is the notation, dy dx. Okay? And we will also use a little bit. And for now, we just have to think that this is not a fraction, it's just the notation. D, like derivative of y with respect to x. Okay, derivative of y with respect to x. That's how we can call it. This is the same derivative of the function f of x with respect to x, derivative of f of x, derivative of f of x, and we indicating this is like more on the calculus free. I don't know if you like the multivariable, then we have x, y, z, and then we calculating derivative with respect to x, with respect to y, with respect to z. That's we don't, they exist, yes, I want you to know, but we will be probably using a lot y prime, f prime, and dy dx. Okay, and if we have to calculate at a certain value, we will say f prime at a. And for this notation, we will just indicate the value a here. Okay, yeah, just this. And now the formula. Let's take a power function, x to the power of n, because we did lots of exercise. Derivative of x to the power of 1, derivative of x to the power of 2, derivative of x to the power of 3. Now, what happened? Let's look at these answers. Let's take them back and let's look, maybe we have some pattern because we're applying the same limit. Yeah, that's mean this is really technical. Now it's like finding the pattern, yes, like a number theory, a little bit. Okay, and now what happened when we have x to the power of 4, 5, 6, 7, just a power function. Power function has x, the formula is x to the power of n, and n is a positive integer. Positive, always positive. Okay, that's me. Now you will help me. Yeah, what was the derivative of x? We know what's the derivative of x, 1, and I'm using the new notation, dy dx. Please just tell me, I have to ask, why derivative of x is 1? Please, I have to, because I know how this will help you because of the slope. Because now I can provide the formula, and then for some reason you even forgot that this is the slope of the line, and because we're applying the formulas, because we like the tools. Okay, now x squared. Do you remember what was x squared? Parabola 2x, thank you. And we did x cube. What was x cube? Who remembers X? Yes. And you can probably see the pattern. Let me do something like this, but this is just, we still think that is slope. This is just for the purpose of the pattern. Do you see how the coefficients and the exponents, the powers, how they change the place and what is happening? When we have x to the power of 1, it's 1 x to the power of, because I can say x to the power of 0. X to the power of 2, it happens that 2 is an exponent, and this is one number less. X to the power of 3, 3, x to the power of one number less. And then can you tell me x to the power of 4? Because we didn't do x to the power of 4. But what about, yes, I can see, Lara, 6. I know what 63 means. Because above the 6 we have the power. Yes, 4x cubed. 4x cubed. And now, what will be the general formula for the power function? And we call power, like power rule. X to the power of n, what is the derivative? Of course, I can write n x to the power of n minus 1. Yes, I mean, now we can quickly calculate. But of course, I have to remove this. I don't like it. We know, we know y is 1. Okay, that means this is the first rule, the first shortcut formula. Power function, x to the power of n, derivative, and this is the nice notation, derivative of the function x to the power of n with respect to x is this, n x to the n minus 1. And please note, I said that in this rule that n could be any real number. Because it's not a power function. Power function has n positive integer. X to the power of 1, 2, 3, 4, 5, 6, 7, and so on, integers. But this rule, yes, I'm not really proving this, but this rule works for any real number, n. Okay, which is not really, it's still called power rule, but it's not really a power function. Because for instance, when we have function, find the derivative with respect to x of 1 over x. That's not power function, but I can rewrite this as a power form. And that's because this is the tool. We have to always use the tool for more tasks. Okay, that means let's actually try. Do you remember we did 1 over x? 1 over x, do you remember the formula was negative 1 over x squared? Hyperbola, I was drawing even the graph. Okay, but let's apply the formula. Let's see. Negative 1 x, and from negative 1, we subtracting 1. Negative x to the negative 2. And when we rewrite without the negative exponent, it is negative 1 over x squared. Yeah, that's we can use it even if it's not the actual power function, but we may rewrite in the power rule. What about square root of x? We also, I skipped the square root of x, but what is the power form for the square root of x? X to the power of what number? 1/2. And the answer was 1 over 2 square root of x. Let's see. Let's apply the power rule. 1/2 x, and we subtracting 1 from 1/2. 1/2 x to the power of negative half, and yes, this will be the form without a negative exponent. Yeah, that's we can see now. As soon as you can get the power form of the function, you can apply the power rule. Okay. And if I will not specify that you have to use the definition, limit definition, you can use the shortcut, quick. Yeah? But I still want you to understand what derivative is, because we focus on the calculation and then we forgot. It's the slope. Okay, let's see what else. Constant multiple rule. When we have a constant times a function, yeah? That's please remember, because what is derivative of the constant? Derivative with respect to x, let's say 5. What's the derivative of 5? Constant, we know what is constant function, horizontal line. What's the slope of the horizontal line? Yes, always think about the slope. Derivative is the slope of that guy, okay? Of that, yes, person inside. Okay, and let's say -5, the same, horizontal, yes, 0. But now, when we have a derivative with respect to x, and let's say 5x squared, of course, we will not even print that dot, but this is different, yes, because that's not really a constant. This is just like, let me write properly. It's just a constant, like we multiplying, yes, we multiplying a function. That's what we can do. We can keep that constant outside and just focus on the variable. But we still have to keep that constant. It will be not 0, only 0. Yes, because it's horizontal line. This is not horizontal line. Yeah, that's not horizontal line. That's mean always, yes, think this is parabola, slim parabola, because each value is multiplied by 5. Okay, that means this will be 5. This is 2x. The final answer is 10x, which you will do right away. You will multiply right away. But just telling you this rule. Constant is still waiting outside, and we differentiating a function. Okay, now addition and subtraction, sum and difference rule. When we have a derivative of the sum, is the sum of two derivatives. Derivative of the difference of two derivatives. Yes, no problem. It's different story with the product and the quotient, but we will cover this after midterm 1. Okay, for now, addition and subtraction only. Okay, and this formula, I have to tell you, okay, derivative, I will not really prove, yes, this is the limit, but it's also a little bit crazy because I think we had this limit in chapter 2. Okay, the good thing is derivative of the function e to the x, natural exponential function, is just the same function. That's how unique and how nice natural exponential function is. I am solving this through the limit definition, yes, I'm using, but at some point we have to evaluate this limit. And this limit is here, and this limit is equal to 1. That means e to the x times 1 is e to the x. That means you can check, yes, you can check in chapter 2, yeah, if you want, but you can just believe me that, because we have to use a couple of ways to prove this limit, because it is 0 over 0. And we can definitely come back in chapter 4, because we will learn another special rule. But yes, just for now, this is the formula, because somebody asked, yes, somebody asked, what is the formula of e to the x? That means e to the x, derivative of e to the x is just e to the x. Okay, that's it. That's the information. Okay, we can skip this one. Okay, let's skip this question because because this one is just applying the power rule. And e to the t is e to the t. You can do it. I want to look at a couple of extra things. That means, yes, now function f is called differentiable at a if the derivative exists. We know this from yesterday, because if the derivative exists, we can call differentiable. It's differentiable on the open interval if it's differentiable at every number in that interval. Of course, find the derivative of absolute value of x. We did this yesterday, yes, I think it was exercise 10 or 11. Derivative exists everywhere, but where derivative does not exist? Please tell me. Yes, at 0. That means f prime at 0 does not exist. What is derivative of this function? Sx is positive, and please tell me what's the derivative? Sx is negative. What's the derivative on the positive axis? Yes, thank you. 1 and -1. Of course, we know why. Okay, we can see because of the slope. Okay, okay, I want to do this one. Do we have time? Okay, let's get the derivative through the formula. Okay, x to the power of 1/3, because we remember this derivative at 0 also is undefined. And we know it's a vertical tangent. Yes, the cube root. Cube root, I can draw it. Please tell me the formula, the formula that we just learned. Yx, and this is, let's call it g cube root of x. And here we have vertical tangent. No slope, no derivative. Okay, let's follow the rules. The rule, power rule, 1/3 x to the power of 1/3 minus 1. 1/3 x to the power of -2/3 cube root of x squared. That means this is g prime of x. And because what I wanted you to see also, when we have this formula, what about the domain? Can we accept all of the numbers? What's the domain? Domain of derivative. Can we accept all of, is this expression, algebraic expression, defined for all of the numbers? Or maybe we are not allowed to have 0 in the denominator. That we can accept everything, but not 0. Yeah? That's what this means. This expression is not defined at 0, but this expression is the derivative. That means derivative is not defined at 0. We knew it. Yeah, we can see how everything is connected. Oh yes, we all connected through the numbers, through quantum physics, through energy. Okay, that means this is also another way to check the explicit formula and look at this formula algebraically, just finding the domain. Oh, 0 is not good for this formula. Okay, derivative is not defined at 0. Yeah, nice, 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 nice. Okay, and I have one more thing. This just to the summary of I think I also mentioned this, but this is the situation where function will not have the derivative. Corners, discontinuity, and vertical tangent. Okay, because we cannot really draw a tangent. We cannot really draw a tangent. No tangent, no slope, no derivative. This one we do have a tangent, but it's no slope because it's vertical. Okay. Okay, I know that is lots of information, but please maybe even go through again the notes or the videos for 3.1, 3.2, and I think I have additional small notes and small video just practicing all together, because it will help you with your assignments. Okay, that's in, please check these 3 sets of notes. Okay? Before, and try to understand, because later we will learn lots of formulas, lots of more like applications, but when we understand the concept, then it's different. Yes, then we see things differently, and I want you to see things differently. Yes, because you are my students, and you have to. Taking calculus is once per lifetime event. You have to remember forever. Okay. Thank you very much, and enjoy your derivatives. And yes, try to digest everything, and next week we will just review. Okay, Lara is asking, yes, I think I reopened module week 5, and yes, explore week 5. You can even take your practice midterm, or you can look also at and not this or this and this, taking a practice and looking at all of the sample. sample tests, yes? Please check if you see the week 5. I believe I made available last night. I don't know if you have access now to Canvas, but the week 5 is open. No. It's everything. It's properly. It's open. Midterm will be open for 4 days: Friday, Saturday, Sunday, Monday. Monday is a due date, but you may take it at your convenient time. It will be open Friday. Yes. It will stay open. It will stay open. Oh yes, we will have a lesson next week because it will be review, and review is really important. If you follow the review notes, oh, you must ace it. Okay? I mean, we know all of the notes are crucial, important. Okay, I will let you go because yes, you stay with me so long and you participate beautifully. Yes, digest everything and get ready for the review. Thank you. Thank you. Thank you. No problem. Thank you.